Okay, so often in physics we'll appeal to prior knowledge, sort of things we should know from previous classes. And this is one such time. This is about to be a projectile motion problem. It starts off sort of looking like standard fluid stuff because we see here a water cannon pumping 100 liters per minute. That is a volume to time, so that's a volume rate of flow. And we need to convert that to standard units of cubic meters per second, which we do by, first of all, converting to cubic meters, which is 1,000 liters, and second of all, converting to seconds. So when you do that multiplication, you get the volume rate of flow in cubic meters per second, and then there's a nozzle that water's coming out of, which is 1 centimeter in radius. So we can use the volume rate of flow relationship to find the speed v. So the area will be pi r squared. Okay, so dividing this volume rate of flow then by pi r squared, we get 5.3 meters per second. .305 meters per second. And now we're asked to find how far the water stream goes. So we visualize here. So we're launching this water stream on a 30-degree angle. And we see that that water then is going to be moving horizontally and it's going to be moving vertically, both x and y motion. Now, for the x motion, this is going to just be found using triangle trig. This is the adjacent side of the triangle, so it is the cosine component. For the y or vertical motion, we see it's the same as the opposite side of the triangle, so that is v sine 30. And we just proceed now to analyze the projectile motion, knowing the speed of 5.305 meters per second. Well, for projectile motion, there's no acceleration horizontally because there's no horizontal force. And we have a downwards 9.80 of vertical acceleration. The water stream, of course, is going to be traveling out of the cannon and then landing over here. And for that complete trip, there's no y displacement because remember, a displacement means a change, and there's no change in elevation. So we can use the familiar equation from physics 11 to figure out how long that took. Putting in zero displacement and then putting in v sine 30. So 5.3 sine 30 is 2.65 meters per second. And then half of downwards 9.8 is downwards 4.9. Solving this for t, we first factor out a t. And we see that there's two solutions. Either t is 0 or t is 2.65 over 4.9. Now this just corresponds to the water that hasn't left the gun yet, so clearly it's the other solution that we want. Let's just check that I did in my head correctly. Yes, I did. And so that's 0.54 seconds it takes that water stream to impact the ground. So now we can come back over here and say, all right, the distance that the water stream traveled, that's the horizontal distance that we want there. And we can calculate that using the same displacement equation from physics 11. So we need the x speed. So that is 5.305 times 30 cosine 866. So that's 4.59 meters per second. And then the object's in the air for a little bit more than half a second. This term, however, though, just disappears because there's no horizontal acceleration. Okay, so that gives us a distance of 2.48 meters. Okay, in class we'll do a problem where we fire a gun, a water gun, not a real gun, sorry, and we're going to try and find the pressure inside here. Now, we will be able to use projectile motion to find this speed because we're going to measure this height and we're going to measure this horizontal distance here and call it the range R. That's going to be a lot farther than that, so this diagram is not drawn to scale. But for the projectile motion analysis in that case, just to help get you started on it, for the x and y motions, at the beginning, there's an x initial speed that we're looking for. The y initial speed is 0 because the water stream is traveling horizontally at the beginning. The y displacement is downwards h, and the y acceleration is downwards 9.8. The x displacement is r. And so knowing h and knowing r, you should be able to find the speed v just using projectile motion analysis. Then you can use fluid theory to figure out what this pressure inside here is. Okay, so more on that in class. Here's another sort of flash from the past, a force analysis problem. It involves fluids a bit and buoyancy. So let's just talk about this sort of problem here. The forces that act on the 8 kilogram, well, the ramp exerts a normal force. The earth pulls straight down. There's going to be some cord tension, and we're told there's no friction, so that's it. On the 18 kilogram, the rope pulls up, the earth pulls down, and then the water pushes up with the force of buoyancy. So those are all the forces that act on the masses. Now, we need to resolve this gravitational force into its components. And gravity is partly pulling this object down onto the surface. I should draw this to scale because it ends up being the same as the normal force. And then partly pulling you down the surface. Let me shrink this one a bit. It looks a little bit too long there. There we go. That's about right. And we need to figure out for this gravitational force, which we know is mg. So m1g, which is 8 g's of force, which is going to be like 78.4 newtons when we work it out. How much is squeezing us onto the ramp and how much is sliding us down the ramp? Well, again, this ends up just being a triangle, okay? And if this is a 30-degree ramp, as we're told, then this angle here, by geometry, can be shown to be the same angle always. So this ends up being the mg cosine theta component, and this one here is the mg sine theta component pulling us down the ramp. So we've got here 8g cos 30, and here we've got 8g sine 30. Now we don't yet know which way this is going to go. We see over here on this side there's 18 g's of weight pulling us down in this direction, but we do need to consider the force of buoyancy here. Now the force of buoyancy would be rho, the density of water, times g times the displaced volume. The object is entirely submerged, so it's entirely displaced, so we get 8.5 liters of displacement. So we get 1,000 density of water times g times the displaced volume. Well, you'd have to divide this by 1,000, wouldn't you? So it would be 8.5 divided by 1,000 to make it cubic meter units. So that is the displaced volume, so I put it in here, 8.5 over 1,000. I notice that the 1,000 cancels out, so basically I've got 8.5 g of upwards force here. Now, 8.5 g in that direction and 8g sine 30 in that direction ends up being 12.5 g, which is less than 18 g, all of which goes to tell me that the system's actually going to go this way. It's going to go up that way, and then this one's going to fall. So we can now write net force equations for each mass, because now we know which way it's going to go. So this one accelerates up, because the tension force pulls it up. It's resisted by the 8g sine 30, and that's the unbalanced force on the 8 kilograms, so it must equal 8 kilograms times A, M1A. This mass falls, so the 18g force has got to win. It's opposed by the tension force, and then by the buoyant force, which we just showed is 8.5 g's of force. And that's got to equal M2A. So solving the system by elimination, which means adding the two things together, when I do that, I notice that plus tension minus tension cancel, and I end up with 18g minus 8g sine 30 minus 8.5g is 26a. So I can just divide by 26 to get the acceleration of the system. And let's see what that works out to. So that's 2.07 meters per second squared. Okay, so that's a little force analysis involving buoyancy, another flash from the past. Here's a final flash from the past. The car is driving around in a circle, and we view it from above. So there's the circle, here's the car. And so sometimes it's going away from us over here, and then sometimes on this side it's going towards us. As a result, an observer over here is going to experience a Doppler shift from the car's horn. But what interests us in terms of the flash from the past is the force analysis. So this is in top view. Let's look at it sort of in side view. So the car is going like this around the corner, and these are its two back tires. So we're looking at the back bumper right there. Okay, so the forces that act on that car are, first of all, the normal force, which pushes up. It actually pushes up on both tires, but on average it acts at the center of mass. The weight, which pulls down. Those are just balanced and not very interesting. The inwards force, the one that keeps it going in the circle, is the force of friction. Whoops, what happened there? That's not good. Okay, let me pause that and clean that up. Okay, there, that looks better. So select pen. Hopefully we're back in business here now. Right, so this is Fn, this is mg, this is the friction force. And we can say that that friction force is the unbalanced force. It must equal ma, but of course acceleration when you're going in a circle is v squared over r. Now friction equals mu Fn, but in this case, as we already said, Fn just equals mg. So you get this relationship here, and this one can be solved for the speed v. Cross multiply the r, that would be v squared, and then you take a square root. Now once you've got that speed, that is the source or car speed, and you can use that to figure out what the magnitude of the Doppler effect is. So this is not core content for the course, projectile motion, inclines, and then circular motion analysis, but it's certainly something you should have seen before, and every once in a while it's worth reminding ourselves of these things.